Okay, in this clip we're going to be talking about curly arrows. Yay, such an exciting topic. What are they? How are they used? What do they represent? How can we interpret them? Now curly arrows make up a big part. It holds great significance when it comes to organic chemistry, and we're going to talk about that today. Students really get confused when it comes to mechanisms when they actually have to use curly arrows, but it's really quite simple. When it comes to crunch time, it all really depends on whether you understand what curly arrows are. Right, okay, so let's get on with it, shall we? There are two types of curly arrows, right? You don't need to be aware of both curly arrows for the OCR AS spec, but I'm going to show you both for the sake of completion. Besides, it becomes really useful when we're talking about radical substitution. Okay, more on that in another clip. Okay, so the first type and the most popular type of curly arrow is a normal. It's just like a normal arrow, except it's got a curve. Okay, it's a curly arrow. It's that simple. There's nothing else to it. Literally, that's all that is. That's a curly arrow. And that's the arrow that you will pretty much almost always use in organic chemistry. The second type of curly arrow is, again, it's a curly arrow, but the arrowhead, there is only half an arrowhead, like so. Okay, it's not complete like this one here. Right, it's only it's a half-headed curly arrow, which is also known as a fishhook arrow. Now, what do they actually represent? Well, the one on the left, the one that you're going to use most often, which is prevalent in organic chemistry, is literally one which represents the movement of an electron pair. So it's the movement of an electron pair. It's the movement of a pair of electrons. The one on the right, simply the movement of a single electron. There's nothing else to it. Literally, that is all they represent. Okay, so how can we use this in terms of in an example? Well, let's talk about fission. Now, I know we've covered fission in an earlier clip, but let's just revisit it, okay? Now, let's say we had a species. It's species A, B. Now, of course, A is covalently bonded to B, which is shown by this bond, I suppose. And this bond is literally, if we were to redraw it in another way, a single bond is simply a shared pair of electrons. A covalent bond is a shared pair of electrons, like so. So, let's talk about heterolytic fission. Okay, let's revisit heterolytic fission. In heterolytic fission, you've got this species AB, and what happens is we break the covalent bond and we form ions, right? You'll remember that we form ions. And the way we show this using a curly arrow is because the dash shows a pair of electrons. What we can do is a curly arrow, and let's say in this particular case, right, both electrons from the bond go to the B. So we just draw a curly arrow originating at the bond. Whoops, I'm sorry about that, folks. See what's up. Fuddled up. Let's try that again, shall we? Right. That's really odd. Right, okay. So essentially, wait, hang on, that looks like a really bad half-headed arrow. I'm just going to do it underneath. It might be calibration. Right, okay, that's a little better. It's still terrible. Right, okay, so we've got AB. And essentially, this breaks the bond because the electron pair from the bond is moving towards the B species. So we've now got A plus, it's now got a formal charge, and B minus, but hang on, we've also got a lone pair of electrons, also got a lone pair of electrons on the B, right? Because that's where the electrons have moved from the bond to the B species. I'm going to change that to a different color because you can't quite see that. Let's change it to an orange. It's a little better. Right. Right, okay, that's all there is to it, okay? The second case is when we've got heterolytic fission, okay? And you'll remember in heterolytic fission that, sorry, I beg your pardon, homolytic fission, that the products formed are both radicals, okay? So let's draw this A, B again. Essentially, all that happens, and this is where we have to use the fishhook arrows, right, in terms of free radical substitutions, right? One fishhook arrow towards the B, one fishhook arrow towards the A, which essentially just forms A, B, and because we've now essentially, because this fishhook arrow shows the movement of a single electron, right, we're just going to have one dot there, A dot, and B dot. And you'll remember that a single dot just means we've formed a radical. A radical is simply a species with an unpaired electron. This is all there is to curly arrows. Literally, folks, this is all there is to curly arrows. Okay, I hope that made sense. See you in the next video.